So the pH electrode is this specifically designed ion selective electrode that's remarkable. And the way that it works is exactly as I mentioned before. You've got two reference electrodes inside of that housing that you've all used before. So most of you use this thing, it looks like this, and then comes out that there's this cable, and you plug that in, and then in that meter you read out pH. That's this thing, right? And so you may be inclined to think that this is just a single electrode in here because there's a single wire, but that's not true. It's an ion selective electrode, which by definition requires two different reference electrodes. In this case, you've got two silver chloride reference electrodes here, and we're measuring the voltage difference between them based on the selective binding of protons in water to its ion selective membrane. The cool part, and so what that means is this electrode thing here that you've used before is really two. So you can see the actual picture over here. So you've got two silver chloride electrodes. One's sort of in the center, and then one is on this coil around the side. So one of them is sensitive to the filling solution on the inside, and then one of them is sensitive to the external filling solution by means or through the membrane. So you can see the full cell diagram here where protons are on both inside and outside, and the junction potential forms between these two things based on that double layer that forms at the interface by a similar mechanism. So this is what the picture looks like. These things they're pretty easy to make aside from the membrane. So the membrane, instead of being a polymer, is actually a thin glass layer, which is why we always say be careful with these things, and also why you have this like plastic protective gate around the outside, because the bulb, that really thin bulb, which is you know, tens of microns thick, about a hair's width thick, is crucial to the function of this thing. And if you touch it on something incorrectly, you'll crack the bulb, and then obviously the outer solution and the inner solution are the same, and you'd measure 0 volts. So let me show you how. All right, so I'm going to show you this quick video from a company that manufactures these things. I think it's a reasonable video.
Potentiometric pH measurement is the measurement of a potential difference using so-called glass electrodes or non-glass electrodes. In the case of glass electrodes, the pH-sensitive element is a glass bulb that is fused to the end of a glass tube. The electrode is filled with a neutral potassium chloride solution buffered at pH 7 and contains a silver chloride wire that forms the electrical connection. The reference system is located in the outer glass tube and also consists of a silver chloride wire.
So the silver chloride wire here is the one that is sensitive to the proton concentration through this glass bulb membrane, and then this is the second silver chloride electrode that's in the outer body of the cell that is just in this inner filling solution here.
In a potassium chloride solution. A so-called junction protects the reference system from the medium to be measured without disconnecting the electrical connection between them. The pH value is calculated from the potential difference between the reference system and the measuring system. Let's think.
Which of course are actually just two reference electrodes, but one of the reference electrodes is sensitive to the junction potential that forms at the interface of that thinly pulled glass there.
Take a closer look at the pH-sensitive glass bulb to understand how this potential difference is formed. Diluted hydrochloric acid, for example, contains large negatively charged chloride ions and small positively charged hydrogen ions. When the pH sensor is immersed into this acid, the hydrogen ions are able to penetrate the boundary area of the glass membrane, the so-called gel layer. The considerably larger chloride ions remain in the solution. The result is a charge separation. The same process occurs.
Notice here that the functionality is similar to the polymer ISE that I showed you before. These protons in solution don't actually diffuse through the glass, just like the C+ ions in the previous video don't actually diffuse all the way through the layer. They just form in what's called the gel layer. So if you take glass, the thinly pulled glass, and you put it in a water solution for a period of time, the first couple nanometers of that will become this sort of viscous gel instead of glass, which is sort of phenomenal. This is really interesting property of amorphous glass. And then the small ions can diffuse into the tetrahedral sites of that that silicate that's formed here. And so you then have the protons on the inner side, and the fact that they're different in concentration is what generates that junction potential.
On the inside of the sensor with the neutral solution buffered at pH 7 that has a constant concentration of hydrogen ions. If the hydrogen ion concentration, hence the pH value on the inside, differs from the concentration on the outside, a measurable potential difference forms.
And by measurable potential difference, what is literally meant by this is in that sort of modified version of the Nernst equation, which I showed you in the previous video, where you have a constant plus the 59 millivolts over N log activity. This is log activity of protons now. So every time the proton concentration changes by a factor of 10, an order of magnitude, we would measure then a 59 millivolt change, because this is N equals 1. This is proton. So what that literally means is that the pH, which is a log term, every 1 pH unit that changes, we get 59 millivolts change. And so when you are using a pH meter, what you're really measuring is a voltage change between the two silver-silver chloride reference electrodes. And then that 59 millivolts is just converted electronically in the meter that you're using. But you can see next time you use a pH meter, most of them have a V setting or voltage where you're reading the millivolts directly, and that's because you're measuring the voltage difference of the junction potential on the electrode instead of converting it to pH.
If the hydrogen ion concentration on the inside is lower than on the outside, as shown here, the measured solution is acidic with a pH value lower than 7. If the hydrogen ion concentration is identical on both sides, no potential difference forms, and the measured solution is neutral with the pH value 7. The measured solution is basic if the hydrogen ion concentration inside.
Okay, with this picture in mind, I just want to introduce a couple different possible errors in pH measurement, and then I'll let the video finish, but I think this is pretty illustrative here now that you understand that it's simply the adsorption of the protons in the outer layer that create the junction potential. But now imagine if you have a really, really low pH, meaning you have a really high concentration of protons, at some point that glass layer saturates. And so if you have a ton of protons in solution, then the accuracy of your pH measurement at very low pHs is not good, because you are reaching saturation of that outer layer. So just know that pH meters are not going to be as accurate in very low pHs, especially below pH maybe 2 depending on the meter, but certainly below 1. So if you're talking about strong acids and you're trying to measure the pH, this outer layer is totally, completely saturated. Another thing to consider then is if you're trying to measure the pH of a solution that has other ions that are comparable in size and charge to hydrogen, right? It makes sense that the reason hydrogen ion can diffuse into this gel layer is simply based on the size of the tetrahedral sites that form in this partially crystalline silicate layer of glass. But if you have an ion that's comparable in size and charge, those are the only differential parameters that are preventing anything else from diffusing into this. So if you've got an ion that's comparable in size, it's just going to diffuse into, and it's going to create the same junction potential between the protons on the inside and in this case, it's masking itself as a proton and pretend. So things like lithium and sodium, if you've got a really concentrated sodium chloride solution and you want to measure the pH of it, you're probably going to have considerable error in that measurement. You won't know, you're just going to read the pH, but know that you run the risk, especially if you've got like a lithium chloride solution, which is common in battery science, and you try to measure the pH of those systems. They're always almost in significant error, simply because the ISE is selective, but it's selective from things that are pretty distinctly different in its chemical properties. Other thing that you probably have experienced and just didn't think about it, and maybe it was frustrating to you, is that it takes time for this equilibrium process to occur, right? You've got stuff that's diffusing from solution into this gel layer. And there's a couple things that can go wrong here. One, if you let this thing dry out, this gel layer hardens and solidifies. And it takes a long time, maybe 30 minutes, for this thing to rehydrate. And so if you have your pH meter out in the air for a period of time and it starts to dry out and then you immediately put it in, you want to measure the pH and it's changing and fluctuating quite a bit, what do you expect? You've perturbed significantly the layer that is the sensing layer. At the same time, you have to wait for the equilibrium to be reached. Equilibrium is not instantaneous. It requires diffusion, macroscopic diffusion of ions to this interface, and then once these ions are at the interface, it's required to diffuse into that gel membrane. And so when you're measuring, it's advisable that you're stirring, you're using the pH probe very carefully so you don't break the bulb, but you're moving it around because that's going to accelerate the mass transport to the interface, so you don't have to wait in a solution that's not stirred for everything to slowly diffuse. At the same time, it takes a certain amount of time, depending on how thick that hydrous layer is or the gel layer, for those things to diffuse in. And so that's why if you put your pH electrode in, it's not instantaneous. Hopefully now you'll have a little bit more patience because you understand the mechanism by which it's sensing, which is phenomenal. But of course it takes time. Equilibrium takes time. Okay, so let's finish this video here.
The glass bulb is higher than in the measured solution. pH measurement with
So I'll introduce this in the whiteboard after this, but I'll just show you this part of the video. So, and I alluded to this earlier, modern ion selective electrodes are actually mostly being transferred to the solid state, which use essentially a transistor geometry. If you've taken physics and you learned about a transistor has 3 electrodes, where you essentially have 2 thin electrodes that you can pass a current between, and then you have below that what's called a gate electrode, and you can modulate the current between those by modulating the gate current below it, and usually there's a semiconductor there, so you apply a voltage below it, it modulates the current. That's an oversimplified definition, but if you go on and take some physics courses, transistors are the building block of all modern technology around us. They're literally every pixel in your camera, phone. They are every logical decision that's made in any computer, any device around you. But if you take one of those out and you sort of scale it up, you can take and use chemicals actually absorbing to the gate to modulate the current that flows through those the solid state transistor, and that's what you're going to be shown here. That type of transistor is called a field effect transistor, or a FET, and that's how many modern chemical sensors work. So this company is just showing you how theirs work.
Glass sensors is based on so-called ion selective field effect transistors, short ISFET.
Nobody calls it that, by the way.
A MOS transistor arrangement, which contains a pH-sensitive layer instead of a metal gate. Positive hydrogen ions forming to be separated on the other side. As a result, the area between source and drain becomes...
So this is the gate layer. Typically, there's an electrode down here in typical field effect transistors that are not chemically sensitive. But in this geometry, you have 2 electrodes on the sides. You can see the wires coming, and we can measure the current through those. And that current becomes slightly modulated based on this sort of yellowish layer that's sensitive to different ions. Here it's sensitive to protons, but as you can imagine, you could design a variety of different solid interfaces that are specific to different molecules. The cool part about this is it doesn't necessarily depend on a charged species. So you can build FET transistor sensors for a variety of molecules as long as you can customize the selectivity of this gate layer. At the same time, people are modernizing these things. Of course, the sensitivity is going to go up if you have a higher surface area. So they're changing these and making them really high surface area, really porous, so that they can absorb more molecules, which then modulates the source drain current even more that way.
Comes conductor. The resulting flow of current is in direct proportion to the pH value of the medium. Just like the glass sensors, the ISFET sensor also needs a stable reference potential. The potential that forms at the ISFET can then accurately be measured against it. The reference system is also protected from the measured solution by a so-called junction.
Okay, so that's it for the ion selective electrodes.